So the topic you already saw in your email is high-resolution spectroscopic follow-up of known exoplanet hosts and candidates with our telescope at Moletai Observatory, Lithuania, which is located 70 kilometers from the capital, Vilnius. And this work is done together of all my colleagues that works in exoplanet and astrospectroscopy group, namely Arnas Drazdauskas, Ašutos Šarma, PhD student, Gražina Tautvaišienė, Renata Minkevičiūtė, Šarūnas Mikalaitis, and two students of mine, Ugnė Janauskaitė and Tomas Narbantas. So as Hilary just introduced me nicely, there is not much to say, just that I will add that I'm Lithuanian, living and working in Lithuania, though I have 2 years abroad work in Lund, Sweden, where together with Sofia Felsing and her group, we worked on deriving the selection function for surveys and binary stars together with Ross Church, that you might know him. And now I'm a senior researcher here at Vilnius University, and also I do start to teach a lot students on basic astronomy courses because our senior professors retired and we have now to take his duties a lot. As well, we organize a lot of summer schools in Moletai, Astronomical Observatory. Therefore, I know some people from Tallinn and from Uppsala, particularly because of many years collaboration between Lithuania and Nordic countries. As Hilary mentioned, I also take part as mentorship coordinator at Exoplanet Society, and recently been elected as a secretary for the society. So for the next 4 years, a lot of challenge waits for Exoplanet Society. And just wanted briefly to introduce the group. We are quite big group in the institute. We are many young researchers. We have 2 professors, Gražina Tautvaišienė, the group lead, and a Ukrainian colleague. He works not on exoplanets and stars, he works more on galaxies, but since he is a part of our group officially, so I added his expertise as well. And we have like 5 senior researchers, including myself and Šarūnas Mikalaitis, whom name you might know, and Erika Pakštienė, and several young researchers, and 5 PhD students, but one is about to finish, so for more PhD students working in our group, in only our group. So let's go to the talk that you're all excited about, the planetary hosts that we are following with high-resolution spectrum at Moletai. So we are all familiar with this nice mass and period distribution that shows that planets around other stars are common, and the planetary systems are diverse. If we had in 1990s only one planetary system in mind, the solar system, the field has changed dramatically, and we needed to change our understanding how planets form. And actually, up to now, we don't really know what is the main driving mechanism of planet formation, because we have those hot Jupiters that are so close to their host stars and super Earths and other planets, and we still see that the Earth-sized planets, even though they are not so populated in this figure, is just a question of time, as in Depeche Mode song, when we will find them. And today we have more than 5,500 planets confirmed, and many more are waiting for confirmation. And we know that planets form in planetary disks, and this nice image of ALMA, when we see the disks forming planets, we must to admit that the key to understand planets lies in the observation of the host stars, because by observing the stars we can find new planets. It's the only way we can find. The most driving way to find planets is just observe the stars. And this is the way how we can learn about planetary properties. By studying host stars, we really need to get the details on star masses and radius if we want to infer properties of the planets themselves, and to understand actually how planets form and how they might be and what they are made of. We really need to know the properties of the hosts. So having this in mind, there are many dedicated studies that you can see on the top of this figure. Dedicated exoplanet missions, space missions. Kepler started this pioneering work of hunting for planets, but now we have TESS and Cheops, and Plato and Ariel is awaiting for many challenges. But there are missions that are sensitive also for exoplanets or dedicated to characterize planets like JWST, that we can learn about the atmospheres, the atmospheric composition of alien worlds that are not similar to what we see in our system. And also we should admit that ground-based observatories are very needed in this field, because it also gives confirmation of exoplanet detection, right? So, but also we being as a researchers in the institute, for example, myself, and having telescope, it's a natural step, you know, when you observe stars. What else you can observe? Also observe stars that host planets and are accessible with the size of the telescope. So what people and scientists started to learn from the spectra of stars, and what we can learn from the star spectra about their planets. And this is a great question that one can ask. But first, let's look at the most cited element, or the composition as metallicity. How metallicity is related with planets that we observe around stars. So it has been shown in the work of Santos in 2001 and Fisher and Valenti 2005 that metallicity is very important, plays a very important role in planet formation. But because, as you can see in the first figure, Santos analyzed stars that host giant planets, as we can see in red, and also analyzed a comparison sample. At that time, the sample was really small, and they found that planet hosts have higher, on average, have higher metallicity than comparison sample that do not presumably have planets. And the same was found by Fisher and Valenti, where we have a higher probability to find the planet around metal-rich stars. So out of 122 metal-rich stars, 18 will be gas giants, as it found by Fisher and Valenti work. So it seems that more metal-rich stars host close-in giant planets, and more metal means giant planet cores forms faster. So it's like building blocks. Metallicity plays as a building block for planets to form. And we know that the planets form from the disk, from the planetary disks, right? So as I said at the beginning, when we just find few planet hosts, we already start to notice this interesting metallicity relationship. A natural step was to look at other type of planets to see if this metallicity plays any kind of role for other type of planets. And later on, Sousa showed this early indication that metallicity for Neptunes do not play that important role as for giants, and they said that Neptunes can form at any metallicity, though from this figure we see only few Neptunes are indicated here. So it means that it's early indication shows that Neptunes can be formed at any metallicity, not preferentially around metal-rich stars as it is shown for Jupiters. So, but at that time, again, we only have 66 planet hosts from HARPS GTO program. Later on, this result was stronger confirmed by other authors, showing that Neptunes really can form around all kinds of metallicities, and even distribution shows that combining the data from GESI and literature, that tends to be more the Neptunes tend to be more around metal poor stars than the Jovanian planets. So different things than with Jupiters. So when we look at even other type of planets, the nice work by Lars Buchave and in 2014, almost 10 years ago, they published results on 400 stars with 600 exoplanet candidates from Kepler sample, where they show that rocky planets can be formed at any metallicity. If we'll see in figure that ice and gas giants on average are more common around metal-rich stars, then rocky planets can be formed at any metallicity, and the average of those metallicities is around 0. But for the ice giants, we see that the average metallicity is around 0.2 dex. So, and the authors concluded that the planet formation scenario as core creation for ice giant is most likely scenario, where higher metallicity means more planetary building blocks can be formed. And the later works also analyze this core creation model for. So only gas giants prefer metal-rich stars, as we can see. So recently, Adebekian and Carolina Dorn was trying to see, is this correlation iron mass fraction of rocky exoplanets 1-to-1 corresponds to stars. And they showed, as you can see in this figure, on x-axis we have iron mass fraction for stars, and iron mass fraction for planets. And they show that the rocky exoplanet composition depends, we have this dependence on chemical composition of the star, but this correlation is not one-to-one. And this reflects the composition of the protoplanetary disk and due to planet formation processes. It is explained in the paper how they calculated this iron content of rocky planets, but it's not that easy to understand and to follow for myself. When we have opportunity to look at the statistics, at the demographics of planets, Pettigura's work in 2018 demonstrated correlation between planetary occurrence rates and metallicity, looking at different planets. As you can follow here, a figure shows the short period planets, and we see that there is steep dependence on metallicity for Jupiters and sub-Neptunes, and flatten for Earth-size and Neptune-size planets. This correlation for Earth-size planets is negative when we go to longer period orbits, and the planets larger than Neptune are an order of magnitude less common than planets smaller than Neptune in this 110 days orbits. And this correlation also steepens with decreasing orbital period and increasing planetary size. So interesting works are happening now when we have more and more planetary hosts. Also interesting results were shown by Debekian and Haywood works, where they demonstrated that most likely that stars that host planets are also enhanced in alpha elements, as they show in this work, that on average the alpha occurrence of different types of planets also may depend on chemical abundance of the host stars. And also they related this that probably those planets are around stars that are in, for example, in galactic thick disk stars, which is like consequence of galactic chemical evolution. We know that thick disk stars are on average more alpha enhanced. And also the role of other abundances of other chemical elements naturally was analyzed, and there is no common agreement between studies if we can see other elements are enhanced in star-shaped planets or are not. Those results are actually changing year to year, I would say. And here we have, for example, Soares and Andres' work in 2017, where they conclude that there is no difference in carbon for stars with planets. The red dots now are comparison sample, which means that the stars do not host planets, and the green and blue dots means stars with planets in different masses planets, and they show that there is no difference between the hosts and not the hosts. But later work by Delgado Mena showed that there might be that there is a carbon enhancement in hosts where they host smaller mass planets. So as you can see, the field is really diverse, and the results are changing with time because we get more and more good data on those questions. And how difficult is to associate metallicity and host metallicity and planetary metallicity illustrates this nice figure where I show you figure on x-axis we have planetary mass by Earth masses or by Jupiter mass, and on y-axis metallicity relative to host star. So the black line connects results for solar system, and the colored ones results for exoplanets. We cannot really compare results very straightforward because those measurements are done using different multiple chemical species, different diagnostics. And in solar system, methane or the carbon is a proxy for metallicity, while in exoplanets, you can see diverse diagnostics to infer their metallicities. So the main idea for this figure is that with more massive exoplanet, we see kind of this one-to-one metallicity relation to the host star, while probably for us, ice giant, this correlation is not very much constrained yet. And we believe that this figure will be filled with more and more results with JWST observations. So going back to work, what we can do in Moletai, having this instrument and high-resolution spectrograph, we decided to follow up, to initiate a project to follow up the known exoplanet hosts that we can observe with our telescope and the potential candidates. So we selected bright stars from the test list that has minimum chemical information from high-resolution spectroscopy. And also this project got finances from Europlanet Telescope Network as well to carry out these observations. So our telescope has high-resolution spectrograph called BUES because of Vilnius University shell spectrograph, and it's been installed in 2016. I put here QR code if you want to learn more details about this, observatory and the instrument itself. So as I mentioned, we do remote observations. The telescope is 1.65 meter telescope, and the spectrograph has 3 resolving modes, 345 and 60,000, and spectral ranges from 400 to 880 nanometers. We have a lot of cameras in our observatory to be able to see the sky, and you can see from this nice GIF that the sky sometimes is in favor of observations, but in the past few months is really disaster. We can't observe. And about the spectrograph itself, here I just put some details. That is a shell spectrograph, and on Skyber fiber aperture is 2.5 arc seconds, and it has uh, as we call it, black box that is in isolated room, lower level from the telescope. And it has also front end module that is attached to the camera on the telescope, and the optical fiber goes from the telescope to the lower level building to the spectrograph. And yeah, here I took a figure from Šarūnas Mykolaitis 2018 paper, where he compared how the solar spectrum with our spectrograph called BUVES compares with other spectrographs. Just want to mention that the other spectrograph spectra were downgraded to match the resolving power of BUES, and the spectra was observed at 60,000. So you can see that it's more or less nice lines that we can analyze with BUES. And as I mentioned, we can observe from whenever we have a good internet. We only need cameras and weather forecast to see if there is no coming cloud coverage or rain. We very in favor of satellite images, a local weather forecast. Actually, Polish weather forecast is also very much reliable. So we put different weather forecasts models to see how our night will look like. And we have another we have a telescope control monitor where we have telescope control window and spectrograph control window and camera control window. So basically four things that we need to care is the weather, control the telescope, control the spectrograph, and control the camera to make sure that the star is not running away from a guider. And we are observing that with this all the night. So we are many observers. As you saw, our group is quite big now, and usually one person is observing one night. We started with more nights, but then we figure out that we ruined our next days. We cannot come back to work that easily, so we just observe one person one night, and some persons can share the night if it's winter night, because winter nights, as you know, are from 4 to 8 or so. So it's good to share if you can sleep half of the night and then to go to observe. So our project aim is to follow up the known exoplanets and candidates, and the main idea is to derive whatever we can derive for those stars. The atmospheric parameters, chemical compositions, and for those planets' hosts. So since we work on CNO abundances for many years with Gražina Tautvišienė, for sure we are deriving the CNO abundances, lithium, magnesium, alpha elements, and other elements as well. So what kind of programs we use, what kind of methods we use to do the analysis? For stellar atmospheric parameters, effective temperature, surface gravity, microturbulence velocity, and iron content metallicity, we use classical equivalent width approach, which is quite fast. We use Tau spec to measure equivalent widths for the iron lines, and to derive parameters, we use Mark's models with Mu code, and we use by now Greves 2007 solar abundances. We use classical approaches to derive effective temperature. We make sure that there is no correlation between derived iron abundance and excitation potential. This rule called excitation balance. For surface gravity, we make sure that there is ionization balance when ionized and neutral iron gives surface gravity value. For microturbulence, we use the approach when there is no trend of iron abundance with absorption line strength. And when we set up all those parameters, this is iterative process, and we set all those parameters, the final product is to run a model with fixed parameters and derive the metallicity as a final product. So we first derive effective temperature, then we derive log G, then we go back, check effective temperature, then we check again log G and do microturbulence and check again all those TEF and log G parameters. So it's kind of iterative process for FGK stars that we work on. And for chemical element abundances, we use spectral synthesis with turbo spectrum, up to 4 lines for magnesium, up to 11 lines for silicon, depending star to star, because some giants and dwarfs or more noisy spectra do not allow to measure all lines. And we use molecular features like C2 span bond heads for carbon, atomic oxygen, forbidden line 6,300 angstrom for oxygen, and molecular nitrogen. We derive nitrogen from molecular features CN bands. And since we work quite many years on the CNO abundances, all the atomic lines and atomic data are referenced in GAI-ISO line list. The latest Ulrike's paper on GAI-ISO line list, Ulrike Hater 2001, I believe is the right reference. So if you need more data on line lists and atomic data, go to this paper. So to mention about spectral synthesis, how it works. So the black one is observed spectra, the blue, red, and green is synthetic spectra. We fit red synthetic spectra best fit to the observed one, and the blue and the green shows the difference of 0.1 dex for the species. And since molecular lines are not absorption lines, they don't behave very nicely. Those examples that I'm showing you, they are one of the ones who look the best. So you really need to go and check by eye all the spectra yourself, because usually if you run this automatically, it will cause you a lot of problem, and eventually you will need and go and check it all by eye. So looking at what kind of stars we have in our sample so far and what is our goal of this project. So now we have this the effective temperature and log G distribution, that's so-called HR diagram for spectroscopists, where you see main sequence stars, subgiants and giants, color coded by their metallicity. So the stars we already have parameters for. And our aim, as I mentioned, is to build a homogeneous catalog with the parameters, metallicities, chemical abundances, ages, and masses of the hosts, and orbital parameters like mean galactocentric distance and height above the plane, eccentricities of stars, and velocity components using open access programs such as I am mentioning here. Like for kinematics, we are using GalPy. It's in GitHub. It's Joe Bowie's code for galactic dynamics. And we are using for stellar ages Unidam code by Mintz and Hacker. This is the Bayesian approach to derive the most probable age of a star, taking into account parsec isochrons. We also derived the probabilistic ratio for star to belong either to thin or thick disk. This probabilistic approach can be either looking only in kinematics of stars, how they move in a galaxy, or looking together in chemical space. For example, if kinematics gives you that star is most likely thick disk star, but its chemistry says that it's alpha poor and iron rich, maybe it's not really a thick disk star. So one can look at all approaches to figure out to which disk star belongs to. So here we see that our stars with planets occupy all ages, and majority of them are the local thin disk stars because they are close to sun. They are reachable with 1.65 meter telescope. This is what we can do from Moletai. And looking at the orbital parameters, the mean radial velocity and maximum height above the galactic plane, color coded by metallicity, we see that stars are mostly on circular orbits, as one can expect from the thin disk stars. So now let's look at the planetary information. What kind of planets we have in our sample that are around our stars. So we end up up till now with 174 planets orbiting 131 star, and majority of them for sure are gas giants, and some 12% mini Neptune-like super Earth, few percent super and few percent of terrestrial planets. So we took this data, we did not calculate it ourselves, neither orbital parameters nor planet masses, which is, I just want to mention, majority of the masses probably will be a minimum mass from radial velocities. All this kind of information is taken from NASA Exoplanet Archive. So now I would like to kind of end and present the results that we have so far. We are still working on those results, but let's have a look what we see. So this is the typical way how spectroscopists will show you metallicity on x-axis, iron, and carbon versus iron on y-axis. I dedicated two graphs for dwarfs and giants, because I know that giant star carbon will be affected by the mixing because the star evolution, right? So we know that giant carbon will be different from the dwarf. Dwarf stars contains the carbon as it was created in their atmospheres. So the yellow dots are from our study, stars with planets, and the circles, the gray dots, are also from our study, but from stars without planets. I did not mention that we started this project not this project, but to observe with Moletai from 2016-17. And up to now, we have a bank of around 1,000 results of close and bright stars. So we can compare our sample with planets, stars with planets, with the results from our own work using the same instrument. So we kind of try to lower the possible errors that can arrive using different studies. So here we're using the same instrument and the same methodology to derive the abundances. So what we can see for the dwarfs, there is no difference between carbon in stars with planets and stars without planets. It just, one can notice that we have in our sample more metal-rich stars that host planets than the comparison sample. But then we can add other surveys like Bensby survey that has also around 700 or 800 dwarfs to see what kind of results we can get. Can we see a carbon, less carbon in metal-rich stars or not? So there's still work to be done here. And for giants, also the same situation. I cannot comment too much more. Just want to mention that here green color is for thick disk stars, okay, that being identified kinematically. And looking at nitrogen, we cannot draw any conclusion for nitrogen because nitrogen line in dwarfs is almost invisible, all right? It's just the nature of stars, and but we cannot see any difference even we have few stars with and without planets. So we are just saying that we don't see any difference between two populations. And let's look at oxygen again. Oxygen, we also, because of the galactic evolution and because of star evolution, we show oxygen for dwarfs and giants separately. And again, we don't see any specific differences, but also we see that again, we have less oxygen for metal-rich stars. It might be some hints, might be not. Let's see what more results we will have in coming month. But also I wanted to say here that to derive those CNO abundances, one also need first to derive oxygen, then go derive carbon, and go back to check oxygen when we are deriving carbon and oxygen and nitrogen from molecular features. I mean, carbon and nitrogen. It kind of irritate process that we need to repeat to check if carbon abundance change oxygen abundance, and then derive nitrogen at the end. The CO ratio now not relative abundance to a sun, but absolute abundance values are very popular in planetary papers. This ratio controls, can tell planetary people the location of the planet in planetary disk, where it's been formed before snow line or after snow line. And one can study this ratio for stars with planets and gain some insights. Again, I'm showing here the results for dwarfs and giants separately. Only another thing that I wanted to mention, this dotted line for iron means solar abundances, right? So for sun, it's a 0, and CO ratio for sun is 0.54 or so for sun. So one can orientate themselves that here stars with planets are in similar composition as the sun, and here is the ones that has lower CO ratio or higher CO ratio at a given metallicity. So natural step to see that CO ratio increases with metallicity. This is a consequence of galaxy formation and chemical evolution. But it's interesting to note that we don't find stars that has this CO ratio higher than 0.8, and some studies have few stars showing that there is this the stars with higher than 0.8, but when I have stars as high as 0.8, you could easily see that spectra are really, the oxygen line is really small, that you could see this it's in between noise to derive this high value. Again, we have kind of for metal rich star, we have this excess of CO ratio for dwarf stars. And also magnesium silicon ratio is another interesting abundance ratio to look, because it for planet formation perspective, it's drive the mineralogy of the planet. So people who does the planet formation modeling, they all the time look at CO and magnesium, silicon, iron to oxygen ratios, to nitrogen ratio. So we also looked at the so-called alpha elements, magnesium and silicon. Again, the gray symbols are from our work that published in Tautvišienė 2022. And the yellows are from 4 stars with planets. There is a hint that we might have overabundance, as Abdebekian and Haywood was saying, that stars with planet are more alpha rich. And I have those surprisingly high silicon and magnesium stars over here, but I'm a little bit skeptic about them, and going back to check if they are just don't want to make any big claims, but yeah. And again, one can look at magnesium and silicon, as I mentioned, ratio, taking those 2 elements by this formula here. And what is surprising, that I kind of by eye see that stars with planets on average at metal-rich side are less enhancing this ratio than stars without planets. Actually, Delgado Mena former work also found that magnesium silicon abundance ratio are higher in stars without confirmed planets. So it might be that this ratio is real. This ratio is real here. And we also looked the ratio dependence on planetary mass. Here I plot carbon over oxygen ratio for different planetary masses. So you can see there is kind of turn down to higher masses. We have this tentative evidence that stars with high mass planets have slightly lower carbon to oxygen ratio, or smaller size planets kind of forms around stars with higher volatile ratio than the giant ones. And as I mentioned, this ratio is important for people who do planet formation. Again, I'm showing only for dwarf stars. So we need to do a little bit correction to include giant stars. We can include giant stars to see if this trend holds also for hosts giants. But we need to account for stellar evolution, galactic evolution, basically, to introduce dwarf stars here. But for magnesium and silicon, we can take all the stars and look what kind of trend we see, and we see a really tiny correlation or tiny evidence that planets with higher mass tend to form around stars with a lower magnesium to silicon abundance ratio. So this is the results from chemical part. It is interesting to see what we can learn from stars about their planets, but it is believed that not only the disk influence the planetary formation, but also environment where stars are in terms of galactic scale, right? So one can study dynamical history of stars. Does it impact planetary formation evolution? I hope that future studies that can observe stars in clusters and learn about their planets can tell us more if the environment, when we have a lot of nearby stars, can influence planet formation and evolution. And there is kind of attempt to look at the dynamical history by studying how stars moves and where they are in the galaxy, what kind of environment there are. But since this our sample is just a local sample around solar neighborhood, we can only infer some from galactic dynamic some things. And here the figure shows where on x-axis I calculated galactocentric distance, and on y-axis I calculated mean galactocentric distance subtracted galactocentric distance. And the closer to the red line stars are, it means they formed where they are now. But the ones who are more far away than threshold -1, they might be the ones that come to the solar neighborhood from inner or outer galactic disk, and it's interesting to see in the perspective of planetary formation. Can we learn anything by studying where stars are and where they come from in the solar neighborhood? So my takeaway message is that stars are very important to understand planets, especially how planets forms, evolves, and spectroscopic results from planet-hosts provide some important information, especially to exoplanet field, and small-sized telescopes can be useful by analyzing high-resolution data, because to dedicate survey to observe stars with planets, one need to really dedicate a lot of time, and only the future instrument with multi-object spectrographs can do this work, I mean, from ground. The ratio of carbon to oxygen, magnesium to silicon that we derived can be used to infer planet morphologies and planet formation models and in galactic chemical evolution studies. So thank you for your time, and I'm open for questions and suggestions.
Thank you, Edita. Okay, yeah.
Thanks a lot.
It was a really nice talk, really clear and super informative. The view of everyone. How can I see everyone? So if anyone has a question,
yeah. Nikolai, I see his hand.
Okay, yes.
So the obvious question is the importance of 3D effects and non-LT effects in how they will affect your results.
So we still did not went to take carefully this question yet. Since as you saw from my results, it's let's see which figure I want to. Can it be oxygen, or it doesn't matter? Since we have a quite metal-rich star, so an LT effect should not affect too much metal-rich stars, though it can affect carbon, oxygen, and other elements. But I recently checked Marcy's paper on 3D and LT exactly for CNO abundances, and the differences between 1D NLT and 3D LT for carbon and oxygen are not that big to say. So I don't know, to be honest, how much it would affect the final conclusion.
Okay, but you have a checkpoint, which is the comparison with the molecular lines, right? You have CO, you have CH. And,
yeah.
So that seems to be consistent. Your analysis is consistent between the atomic lines and the molecular lines. Is that?
So we did not measure carbon for atomic lines. So we only use this molecular feature.
Yeah, sure. Yeah, I understand that, of course.
Yeah.
Yes, but you try to compare carbon across different molecules, right? Yes. Okay.
Yes.
Thanks for a really nice talk. I really enjoyed the combination of large scale sort of overview and then the details of what you're working on. I wanted to ask about the sort of challenges of working with the data you have from Moletai. What is the quality of the data that you have, and to what degree do you have sort of automatization or reproducibility in how you're processing, doing normalization, things like that might affect the final parameter analysis and abundance analysis.
Yeah, so as I said, we are quite big group, so we have dedicated persons to do the same analysis all the time using the same code. So one person does this raw analysis when we just extract spectra, order subtraction and flat fielding from the raw spectra to the scientific spectra, and other person is doing all the time the atmospheric parameters derivation, and it's I mean, the data is quite decent. The errors on our abundances on the parameters are the same as in other surveys like IESO survey, and so I believe, not I believe, I know that it's reproducible, right? So we have this routine to derive automatically parameters. We did many runs for GAIA survey, which involves many more data, many more spectra, 100,000 spectra at once. So we know where to look at those eyeballs, to take a sample and compare. So once we run the parameter analysis, we compare our results not only to the spectroscopic. First of all, we compare to the Gaia satellite temperatures, then we compare to, for example, other spectroscopic surveys that we are on the right scale, that our results are not showing nonsenses or so. So it's on the part of the parameters, we really kind of learn our lessons in GAIA survey, which is a big survey that was run by 300 different scientists, many different nodes using the same tools, almost the same tools, the same parameters to derive homogeneously way. So kind of it's all automatic. And then what it comes to abundance analysis, we do, first of all, automatic determination, but as I mentioned during my presentation for CNO, we really go line by line. Dedicated people go and check by eye what is derived automatically way. So it's yeah, when we need to change the continuum, we change. If we see that the continuum do not work for this molecular line at this particular wavelength, so we change it, because star to star is not the same, right? So we have cooler stars and hotter stars in our sample as well, not only one type star. We need to adapt our automatic tools to this as well.
Okay, thanks. Maybe some of our students also have questions. Quite a few students on the call, actually.
Yeah, and what comes to stars, FGK spectral type stars are dwarfs or giants, especially dwarfs, are nice to analyze. But when it comes to cooler temperatures, M spectral type, when we have a lot of molecules, then it's a really headache and more challenging work to do those cool stars, where we expect a lot of small size planets in the future. So we need to train and learn how to do cool stars to get cool results in future. So it's also a big step.
I have a question. So in one of the plots you showed a dip towards the higher metallicity for C-bio and also for magnesium silicon. Yeah. Or sorry, not metallicity. So
Planet mass.
Yeah. I have two questions. One is, if the host have more than one planets, how do you decide? And
Yeah.
do you have an interpretation of why this dip occurs in both C-bio and I guess magnesium to silicon ratio?
Yeah, so it's a good eye that not all the stars have single planet. So here we plot maybe not very nicely, but you can see the repeat dots. So what does it mean? That it means that the same host will have several planets. So for several planets, we give the same host abundance. Okay. Okay, or
Yep.
one can take the minimum, the smallest planet in the system, right?
Mhm.
And give a mass for the smallest planet.
Yeah. So my second question was then, why do you think this dip occurs and for both C-bio and also for, I guess, magnesium to silicon?
So it's still a little bit hard to tell, because it seems that giant planets just can form around the stars that has this smaller value. It's just either it is, but the data is not still, like sufficient enough in terms of the number. We would like to have more planets, more stars with planets, to say that this is real, right? Because other work do not see this behavior for CO ratio. Magnesium and silicon, Delgado Meda in their sample see this magnesium and silicon ratio is smaller for giant planets, but they don't see in CO. So one need to be very careful when it comes to any conclusion here yet.
Okay, thanks.
Yes, Mikael?
This is just following up on your discussion from now. So I have two, well, one is a comment and one is a question. The comment is that maybe it would be interesting to look to consider all of these planet masses as lower limits and look at the total mass of the planetary system, total known mass of the planetary system, or maybe the total known solid mass of the planetary system, rather than one planet. So then if you have multi-planet systems, the more you know about the total mass of those, like you might reveal it would be maybe more surprising to find a trend with the mass of any single planet in a multi-planet system, right? For that to be a trend, that would seem strange, or perhaps, but the total mass of the planetary system would seem indeed like more relevant quantity, perhaps. And the other thing is, I was wondering if you had looked at the significance of this trend for the carbon abundance relative to hydrogen and oxygen relative to hydrogen, to see if maybe the trend in the ratio is spurious or if it's systematically due to one or the other element. I'm sorry if I missed it.
Okay, so as you suggested, we really need to do this more quantitatively. We need to do statistical tests that we are now trying to do. And or one can also, add more data from other studies. Just make sure that CO values are calculated using the same solar scale to the same solar value, and adding more values, as here we show gray dots from our previous study. So implementing putting more weights to this plot, right? Yeah, so we need to do this when we are doing this quantitatively, but to say if we see this approach. And yeah, and I forgot what I wanted to say more. Sorry. So it's still a lot of work need to be done. We need to look at possible 3D effects. We need to look at the error budget in our studies to drive final conclusions. We need to put errors to make this slope be dependent on the error of each abundance measurement. And I think I did not look at the carbon to carbon over hydrogen ratio versus planetary mass, but I expect it to beat a little bit there, because we kind of see that the dwarfs, there is a dependence on metallicity. So yeah, but I will look to your suggestions. Thanks.
Oh, wow. Yeah.
Your abundance uncertainties are 0.1 dex, right?
For some elements, yes. Yeah.
I just noticed the time. It's already 6:20. But it was it was a really interesting talk, and I personally have a lot of thoughts in my head, and hope I guess we have to end this session now because it's late. But yeah, thank you so much, Edita, and I really look forward to the paper coming out.
Oh yeah,
once when it's when you submitted it.
Yeah, me too. Thank you so much for inviting to your group. It was my pleasure to tell what Lithuanians are doing with the small telescope. So we are using our telescope as frequent as we can to do some science. So thank you so much.
Okay.
Thank you.
You.
Yeah. Bye.
Thanks.
Goodbye.
All right.
Bye.
Bye-bye.